Professional climbers. That's what I started this for.
How's everybody doing? Good? Homework almost done? Getting there? Good. See like some like hopeful faces? I posted the second homework assignment. Only 2/3 of it. Last year when I taught this, I only did a homework assignment on TensorFlow, and this year I'm really feeling like I should have one very similar to it with PyTorch as well. Everybody's using both. In fact, so many people are switching over to PyTorch. Like, I should probably have a PyTorch one as well. So, anyways, 2/3 of the assignment's up there, and I'll get the PyTorch one put together. But that's not due until October sometime, so don't even think about it. Take a breather after finishing this one. The one on TensorFlow, the one that will be on PyTorch, is just like, hey, here's how you use these things. And then the other one is very much like the ones that you've been doing, but they're fully connected networks. Like program all this and anybody feel like they're running anything during the homework? Wait. Yeah? That was a quick oh yeah. That's awesome. These are good homework assignments. I totally stole them from Stanford. Stealing's kind of not true. I actually asked for permission to use them. I just thought they were just really excellent for like getting you to like program. You know, think about programming wise, how neural networks and how all these things, like how the frameworks like TensorFlow and PyTorch, like more or less work under the hood. They obviously don't use NumPy, but you get some flavor of that. You get some idea of like how to optimize some of these things. I just think they're awesome for that reason. Okay. Today starts fun set of lectures, I think. Let's see. It's going to be 3 parts. I think I already mentioned this, but 3 parts. We're going to go through kind of a, like it says, a brief history of convolutional networks. We already started it. We already talked about LayNet as being kind of the first successful one. But we're going to go to ResNet. It should say from LayNet to ResNet and beyond, because we're actually going to go well beyond that. I'm sure there are other networks that we're going to use after that. But I don't know, it kind of has a nice ring to it, right? From LayNet to ResNet. But I think this is really good because like we're gonna see a lot of architectures and we're gonna learn a lot about things along the way. We're gonna learn about regularization techniques like data augmentation, dropout. We're gonna learn about non-plain vanilla stochastic gradient descent algorithms. We're gonna see how those were used in some of the training, some of these networks to win the ImageNet classification competition. We're just going to bump into a lot of things along the way, and by the end of next week, I think you'll if you haven't really been introduced to convolutional networks before this class, I think by the end of next week you're going to be like, oh, I have this nice survey of all these things. You may not know everything about them, but you'll know what's out there, and you'll know some of the state of the art when it comes to classifiers for image data. Okay, any questions before we get rolling? Okay. LayNet. We talked about this already. Why is it called LayNet? Oh, thanks. I always forget these days. Why is it called LayNet? Yeah, it's always like the first person's name, the first author's name. Anyways, just very basic. There's convolutions, and then we go to some more connected layers, and then we go to the output of trying to predict. Oh yeah, I forgot to mention that there's these subsampling right here. These things that say subsampling. These are proving layers, like we talked about last time. Yeah. So. Let's see, what does it say about these? Were 5x5 size filters, stride 1 all the way through. Oh yeah, I forgot about this. I think this is interesting. Anybody ever heard of the MNIST data set? It's like one of the standard ones that is used kind of still, which is crazy because it's so simple, but still for proving that your convolutional network or idea works. It's a set of 70,000 handwritten digits. And well, I guess actually this is not just the numbers. So what I just said to you was like the number subset of this. There are letters as well. Anyways, this is actually where this was first introduced, where they modified it. So anyways, yeah. So it really is a history lesson. Anyway, very simple. Convolution pool. Looks like it should be the convolution pool. The picture shows doing that one more time, but then going fully connected. Anyways, just like everything we talked about last time, no other tricks than that. Okay, so MNIST, that was there are a couple other kind of basic data sets like CFAR 10 that were introduced. CFAR's got like a CFAR 10 and CFAR 100. Can't remember how how many classes it gets up to. But there were these kind of small data sets that were used to prove out convolutional networks. Not only were they small in the number of images in this set, they were also small in like the number of like the pixel size, so like the height and width. But then a bunch of researchers got together and they're like, you know what, if we're going to move this field forward, we've got to get together like a real data set. So they scraped Flickr, I think is what it is, and they put together 14 million images with 20,000 classes in them. And to be honest with you, I'm not exactly sure how they decided on which classes or whatever, but this was like pure Mechanical Turk, people sitting down and saying, like, here are the 20,000 classes, which class is in here? Probably was done the other way, where it's like, here's a bunch of images, let's filter this out to like images that have just like one thing in it or something like that, one object, and then like, here's the object. And then for some reason there was like some dog expert who had all the subspecies of Saint Bernard and things like that. But the point was that they put together this enormous data set, got it labeled, and now now you've got something like to really prove yourself on. And competition started in, what was it, 2010, I believe it is. Competition started in 2010 on this image set. Every year, this was announced at CVPR, one of the major like computer vision machine learning conferences. They would announce the winners of the challenge, and we're going to see a chart of like what all the accuracy or the errors were on this set for the classification tasks. There's actually a number of tasks. They kept adding labels to it. It's like it was like a localization task. They bound things in the image and say, not only tell me what object's in there, but where it is in the image. But anyways, you now have, you have these. So you'll see this acronym, ILSVRC, ImageNet Large Scale Visual Recognition Challenge. So of all those 14 million images, 20,000 classes, they carved out a subset of roughly 1.2 million images and 1,000 classes only, and created a competition on that. And this really, really drove innovation. I hope my next, right, good. So, so starting in 2010, they had winners. And so what you're seeing here is this chart of the winners of the classification challenge on that data set from 2010 to 2017. In 2017, they decided to stop. And they said, we're not doing this anymore. We need to do something else. Because you can see in 2010, you start with, so what you're seeing here is the top 5 error rate. So the way this competition decided to measure to measure how well these models were doing was to carve out a test set and then to report on. So all the models would report on the top 5 error rates. So and then if you look at the papers, they report on more than this. The top 5 error rate means the following. These are classification models. If you think about like our softmax output, it's basically predicting. It's giving a probability to each class. So if you rate those from like highest probability to lowest, you can say like the highest probability is like the class that you think you have highest confidence it is. But you can also say like I think it's in these 5 classes. You can take the top 5, like there's top 5 probabilities, whatever those classes are. And you can say okay, if it's in here, if it's in these top 5, then I've done it right. I've done this task right. And so this is actually measured on that top 5 error rate. So it's like 1 minus the accuracy there. So like the number of the number of errors it's making per size of the test set. So it doesn't mean that it actually got it right, like its number 1 prediction was right. It means that it existed in its like top 5 predictions. It means essentially you could whatever the model was, you could submit 5 guesses at the class, and if one of those was right, you got it right. And this is the rate at which you got it wrong. So you can see, like really rapidly, it goes from in 2010, 28.2% error rate. So it's 28.2% of the time in the test set. for a test image. It wasn't amongst the top 5 guesses. If you look at this, you'll see this goes from 28.2. I mean, it just keeps going down. 28.2, 25.8, 16. And then right here you get 16.4. And this is. So these two right here, these two entries were not like deep networks. I think these were both based. I'm actually not exactly sure what the models were, but I think they were based on like bag of feature kind of models, like image feature kind of models. But here you have the first convolutional network winning this thing, and then it's convolutional networks all the way through. And the one thing that's not a year here is just this thing we talked about last time, the error rate that a human will make. So again, like you have to, do Mechanical Turk to label this thing. You also do Mechanical Turk to like to go through and like have some people guess, and then you average that. And that's the average rate at which a human is making errors. Again, top 5 errors. So in 2015 is when we first break that we do better than humans at classifying these things. So that was a real big breakthrough. That was we'll take a look at that model. That's ResNet. So that still is thought of as like a kind of state-of-the-art convolutional network. Although there are variants of it that people use more, I think, nowadays. But it was a big deal that year that it won. It was a group at Microsoft Research. That was the same year that Microsoft they had a couple of other really big things. What was it? They won like the let's see, like they won the parsing. Let's see, what was that? I can't remember. It was also the year that they had Tay, I believe. Remember Tay, the bot on Twitter?
Oh.
I mean, that might have been a little bit later in the year, like in 2016, but it was around the same time. So Microsoft had a whole bunch of AI successes and one big AI failure. If you don't know who Tay is, you should look it up. But not safe for work, for sure. Language in there. Basically, a bot that Microsoft put out there that like people figured out really quickly how to turn it into like a racist, Trump-hating, like person. It was really terrible. They shut it off after a couple of hours. Okay. Anyways, so what we're going to do is do a stroll down memory lane here. We're going to basically go through like all of these models. Not this one. This ends up just being like an ensemble of existing models, and then this one, and then there's other things to talk about beyond this. But just going through the winners of this competition gives us a really nice understanding of like how convolutional networks have evolved from later. Okay, question, yeah.
So why? It seems that like we improved the viability of convolutions like a long time ago before this. So why was it that convolutions weren't prevalent, I guess, like before that? Because
yeah, so like if you take LayNet and take something like LayNet and train it on ImageNet, or the classification channel subset, it doesn't do well. It's a really like that model is the capacity of it for learning is too low. You had to get something better than that, and that's we'll see what that is here.
So people were trying to use convolutions back then, but
they just weren't winning. That's right. Exactly.
There's also like some issue with like IBM holding patents to certain like I don't know if they're like deep learning or convolutional neural net. So like Kuhn himself wasn't even working on this kind of stuff from like 96 to like or like I think it was like 95 to like 2005 or 7 years, something like that. So there's a bunch of other stuff that happened as well.
Okay. So then some like lawyer wants in the case, and then
I think he just sort of worked. Like I think the company got bought, what I remember, and then he just thought or IBM was like part of like a merger, and then like kind of just disappeared, and was like, yeah, this is gonna expire in like 5 years, and I don't think they know that they have this. So we'll just
interesting. You should look that up and bring it to us, like or send us a link and Canvas just thinks it's an article on that. I've never heard of it before. Yeah.
So for these 14 million images, they had 20,000 classes. Does that mean an image could have multiple classes that were correct?
No. So for this challenge, you have just one. You have one class. So it's just a subset of the. It's a 1.2 million image subset of the 14 million like actual folders that and there's only 1,000 classes. And one of the criteria for the subset was to make sure there's just one object in each image. Yeah. So there's like one right answer. Okay, let's start going through this. So here's AlexNet. We've already seen AlexNet. We're going to talk more about what it actually is. You always know that it's AlexNet because the top's cut off in these images. You might notice something else that's really weird about it that you maybe, if you've been looking at pictures of convolutional networks, you might look at this and go, like, what's going on here? It's like cut in half. Not just like the top's missing, but like all of the filters are sort of cut in half, right? There's like a top set of feature maps and a bottom set of feature maps. Right, so we'll talk about that. That's actually due to memory limitations of GPUs in 2012. They had to basically train like some of their filters on one GPU, some of their filters on another GPU, and then every once in a while they got merged. I have a slide on it, so we'll get to it. But this is not typical to see this kind of thing anymore, but we have to do it. This is the architecture. So there's first a convolution. There's a convolutional layer. And we're going to go through the sizes of these. I believe this first one's, yeah, it says right there, it's 11 by 11. So they have this 11 by 11 filter in the first, or set of filters in the first convolutional layer. Then it does max pooling. I believe it's just 2 by 2, strike 2, but I have these. They have this. They have a normalization layer next, which we won't get into the details of. It's a normalized response layer. No one uses it anymore, but they were using it to do some sort of normalization. The thing that kind of has replaced that is something called batch normalization, or layer normalization. Then we followed up with exactly the same set of layers: convolution, max pool, and normalization, and then 3 convolutional layers, another max layer, and 3 fully connected to what should be an output of 1,000, size 1,000, yeah. Because there's 1,000 classes. So that's going to be like your softmax output. And you see how it says things like max pooling, and you see how it says dense here. Dense is like another word for the fully connected layers. In fact, in most of the debugging frameworks, you'll have a dense layer, and you would use that for your fully connected layer. Okay. So let's see if we learned anything from last time. So the inputs to these are images of size 227 by 227 by 3. Okay, so the first layer, the first convolutional layer, used 96 filters of size 11 by 11, and of course by 3 as well. We kind of are lazy about dropping the channel dimension off this, but they're 11 by 11 by 3 filters, and they're applied with stride 4. So the question is, what's the output volume to the next layer? Like, what's the size of the feature maps? And you already have a hint there. You have that formula from last time. 227, you subtract off the filter width, you divide that by the stride, you add 1 to get that, like that middle pixel in, and you get 55. So what's the output? Someone be brave and say it.
55 by 55 by 96.
Nicely done. You're on it. Well done. Good. That's exactly right. So that formula gives you the spatial extent of the feature maps, or we would call them activation maps. Feature maps is the output from this convolutional layer. And we're saying already there's 96 filters, so each one of those filters gives us a channel in the output. So 55 by 55 by 96. What's the total number of parameters in this layer?
96 by 11.
Good. That's exactly right. We forgot the 3 last time. Remember this time. That's awesome. Yeah, exactly. So each filter is giving us 11 times 11 times 3. That's the width, height, and depth, or the channel size, the number of channels. So that's how many parameters in each filter, and there are 96 filters. So that's not approximately, that's actually equal to.
So I remember all the filters, they share the same parameter value, yes.
Not all the filters. No, each filter is different. Yeah, I mean, they have the same sizes, but each filter is different. That's really important, right? That's how you actually are learning something here. You're learning like each one kind of learns like a different statistically spatial pattern. If they were all the same, that would be a waste of capacity in the network. I don't know if that was a question or a statement or something like that, but hopefully that clears it up. Cool. Okay. So next we have pooling. Okay, so it's 3 by 3. I said 2 by 2, but it's 3 by 3 pooling applied to the strike 2. So what's the output volume of this? So this is giving us the spatial extent of the output. We have 3 by 3 filters. They are applied to the strike 2. So in this case, because we're starting at 55 by 55, we're going to go. This goes to 27. So what's the output size? So you know what the spatial extent is, right? 27 by 27. So the question is, what's the depth? Yep. Good. Yep. You just do this. You're just doing this for each of the channels. You're only reducing the spatial extent in the pooling, not the channel depth in any way. So the pooling so we just look what's happened just in two layers here. We started with 227 by 227 by 3. By using the 11 by 11 filter sizes, we go immediately from that to a much smaller spatial extent. We do have a lot more depth because we chose so many filters, and that's good. This is what this is all about. It's like you're learning a bunch of different, statistics, spatial statistics of these images. And then we do the pooling in this 3 by 3 way. So now we go even smaller to 27 by 27, but we haven't reduced or changed the number of channels. We're doing that at each channel. So the question here is how many? Yeah, you have a question before that?
I was just wondering, so if we choose 96 filters, it basically means that we're trying to pick out 96 sub-features of this image, right? That will later be compiled into a greater prediction.
Yeah, exactly. So it's like, the way to think about what's happening in each of these feature maps, each channel, right, is just, it's something about whatever filter's been learned. Remember how we saw those pictures like edge detectors or texture detectors or something like that? It's just basically applying that all the way across the image, right? And the output from that channel is just, each entry in that is some expression of how much that filter looked like that part of the image, right? So because it's a dot product, if it's 0, I mean there's a bias as well, so this isn't quite right, but if just imagine the bias is 0 right now. If the dot product is 0, you essentially have a pattern in that part of the image that's orthogonal to that filter, right? And if it's very large, either positive or negative, it's something that looks a lot like it's very aligned with it, right? And if there's something in between, it's like there might be some of this pattern or not, right? So it's just whatever learned filters are, it's just kind of saying, okay, everywhere in this image, this is how much I look like this filter. And that's the output, plus a bias.
Awesome. So how does each one get a different feature if they're all basically getting the same data?
Because it's trained by backpropagation. So your loss function is saying make this smaller. So this classification task, the loss function is expressing how poorly the larger the number, the worse we're doing, right? We want to make it smaller. So it's just backpropagation that changes the weights. And
so if the minimum of the loss function is creating 96 different features as opposed to just
If that's useful
one of the
for,
same.
if that's useful for lowering the loss,
Okay.
and that's what happens. Yeah.
Awesome.
And that's why you don't see necessarily features or filters being repeated, because it's advantageous if you can lower your loss if they're different from each other. Now you could get stuck in like weird minima and things like that. It's not, but you don't usually get stuck in weird minima, like I already said. Okay, back to the, do you have another
Are
question?
the biases the same across all of them, or are they?
No, one bias per filter. So each filter's got its, it's got its whatever. In this case, 11 by 11 by 3 parameters, and then one more for the bias. Good question. Yeah.
Did we add that in?
We didn't add that into our parameter. We should have done that. Yeah.
Yeah, so how do you guarantee that the filter we will not end up with just a very similar filter? Because it is very
There's no guarantee. You're saying what you're hoping. This is part of the hyperparameter search in terms of like the capacity of your network, like how many parameters are in your network. So if you have a huge data set like this with a lot of stuff going on in it, you're probably going to need kind of all your parameters to do well on it. So you don't get repeated. You just, as a rule, don't get repeated filters because a repeated filter would mean that you're using a capacity to basically just repeat a measure. You don't want to do that, right? If that changes slightly to something else, you're likely to have learned something, like have reduced the loss. So it's usually, but if you do get a lot of repetition or like lots of zero filters, that means that the capacity of your network is too high. It's just not using. You can't use these to learn anything.
okay. That
Or like they're randomized in some weird way. So that is like a way to kind of like debug the capacity of your network. But
it is possible to have zero filters.
it is possible if like you initialize in such a, like if you initialize near zero and there's never any gradient getting to some of those filters. Yeah, thanks. Okay, back to the question at hand. Max pooling. What's the number of parameters in this layer?
No.
Good, 0. There's no parameters in pooling. And that's why it's like a really useful, very efficient spatial extent reducer. It has no parameters to learn. Great. Okay. Good. So here's the rest of the architecture all the way through. So we already talked about the first couple here. You have a normalization layer that's going to preserve the size. And then now we go to 5 by 5 filters here. There's 256 of them, right? So we go from this 27 by 27 by 96 to, so notice what we do here. We have a stride 1, and we pad with size 2. So that actually, because it's a 5 by 5, that actually preserves the spatial extent, right? We don't skip any pixels because the stride is 1, and because we pad with size 2, we can get our 5 by 5 like right into the corners and all the edges. So we actually preserve the spatial extent. So you see that 27 by 27, and you get up to 27 by 27. What we are learning here is 256 different filters. So each of these filters is 5 by 5 by what? Yeah, good. 5 by 5 by 96. It's the number of channels in the input to this layer. And there's 256 of them, so that's how we get 256 of the output number of channels from this layer. Does that make sense? Okay. And then this just keeps going. So then we do, again, max pool, 3 by 3 filters at stride 2. So we go from 27 to 13 by 13. Normalization layer, preserve that. Then we're using 3 by 3s for a couple of different layers. Stride 1, pad 1. So we're because it's 3 by 3, we're preserving the spatial extent, but we are just changing the number of filters, number of channels. And let's see. We finally max pool one more time. 6 times 6 times 256 is not 4096. Is it? Because these are powers of 2. it's like 9, it should be like 9 times, or 9 times,
9,200.
yeah. I mean, it doesn't seem right about that.
Why would they should be 490? Is there fully connected unit?
Oh, I guess let me see, what do we have here? Oh, right, okay, sorry. This is the output size. Yeah, sorry, this is the output size. So this is, sorry. So, yeah, so what's this number? 256 times 6 times 6?
9,206.
Okay, so this tensor gets stretched out into a long vector, and then there's a fully connected layer from that to an output of 4096. Then we go from 4096 to 4096, so some nice square matrix of weights, and then we go from 4096 to 1000, and that's our output that we would send to the softmax and send to our cross entropy loss. Okay. Questions?
How do they come up with this structure?
I mean, we're not them, so we don't know, but they likely played around with a bunch of different kind of like ideas around this, and this somehow was like the best.
For example, if my network is not giving me like the specific kind of output that I'm looking for, then where to start debugging my code? I mean, where to start?
Yeah, it's a hard question to answer.
Jeff Hinton probably just solved this one.
So the way that you typically, like especially like a fairly simple network like this, the way that you would typically think of this is you'd start with like very simple, okay, probably something like the following. You would have maybe a couple of things like this, nothing like this. Maybe really quickly go to 1,000 neurons, and then you get some sort of output. You get your accuracy or your top 5 error. Okay, and then you would maybe within that you tweak a few of the like numbers of filters and stuff, and just kind of compare each time, see how it compares, see which ones seem to be doing better on average. Then you start expanding your network to have more layers. And especially in these days, before there was like a lot of thinking about initialization, you would spend a lot of time, getting like these kinds of numbers right, and in particular, getting the learning rate right. And then you'd hopefully kind of see that things were improving it as you like added convolutional layers, right? So like if I added one, things got improved. So let's add another one. Oh, like they improved. Let's add another one. Oh, they improved. Let's add another one. Oh, maybe it didn't improve so much. So let's not do that. I mean, it's hard to say. It's a lot of experimentation. It's very empirical.
So I'm confused how the third dimension goes from 256 to 384. So we're applying 3 by 3 filters. So since we have 256 layers,
these are 3 by 3 by 256, right? And then we have 384 of them. So each 3 by 3 by 256 gives us one slice, one channel in the output, and we have 384. Okay, yeah.
So I know that we're not going to tell you that okay, I will take this or that.
Yeah.
But this idea of like bulking up that final dimension of time and then taking down the first two. What's the method for that? Why is that so successful?
What do you mean bulking up? You're like getting up to like 384?
3 in the first channel, or in the input, right? And then when you take this last dimension, and that gets much larger, and then first you get much smaller.
Oh, I see. Like the trade-off between like the spatial extent and the number of channels.
What determines like whether we want to make it?
So like this is a very standard like progression of like the spatial extent and the number of channels. And you'll see like this gets much more drastic as we go into much deeper networks. And the idea, right, is that you're trying to take this whole image and like boil it down into like something that is just something small that is like saying, hey, there's a cat here, and the way that it does that is by, you don't need to have a very large spatially extended feature map to be able to say like, hey, there's a cat in here. What you need is like a whole bunch of features. Think of each one of these as like its own feature, like giving you a spatially extended output. And you need a whole bunch of features that's saying like, hey, like this is when a couple of these features come together, we have cats, right? So it's like you're really abstracting from all the pixel details here to something that's like, when you get to here, that really has very little to do with the original arrangement of the pixels, except for like maybe, I mean, convolutions are definitely this way, where like, if something's happening like in the upper left-hand corner of this, it's indicating something about like the upper left-hand corner of that, but you're just really reducing it so that you don't have as many parameters for one, and that the features are becoming much more abstract here, and like kind of like losing spatial information and gaining like class information. And the more of these features you have, the more of these channels you have, like the more you have to make these decisions.
Sure.
Yeah.
Are these interpretable by humans?
Not really. Not when you get deep down here. Although I will show you a video in a couple of weeks when we talk about thinking about how to interpret these, where you can get some notion of interpretability, like a little bit, for like one or two filters. And again, it's empirical, like it's not like determined beforehand. But I'll show you a neat video done by a friend of mine named Jason Wazinski, and yeah, it'll be cool. You'll get a feel for that. But yeah, like if you were looking at them, you'd be like, I don't know what these are. Okay, yeah, one more.
You said that they have a split their network, so that
Yeah, I'll get that here in just a second, like the splitting, yeah. Okay, so let's go through what was cool about Alexander. So like this is not too different from LayNet, right? It's a lot bigger, way more parameters, but it's not that different from LayNet in the fact that it's just like convolution pool, convolution pool, convolution pool, so forth. I mean, that's not that different. But there were quite a few interesting things used here. So this is the first use of Regularization. So you can thank Alex and his buddies for Regularization here. So super successful use of it. I mean, it's not clear, like from the paper, how much is greatly contributed here, but yeah. So it's one of the components used in this so not using sigmoids, not using tanches, using regular as the activations. So that's awesome. We already talked much about that. The normalization layers were these local response normalization layers. We won't spend time talking about them because they're not used, but that was kind of innovative at the time. Another thing that was done here that has really nothing to do with the architecture is this idea of data augmentation. We're going to spend a little bit of time talking about that right now. So remember our discussions about regularization, right? So you have your loss function, and then you can regularize it. And we talked about how regularization is like some notion of how we want the weights to behave or look, right? Some property of the weight. So, L2 and L1 and the combination of L2 and L1 were all preferences for smaller weights over larger weights. And that, you remember like L2 regularization promoted like dense, kind of distributed weights, while L1 regularization promoted sparse, so like lots of zero weights or close to zero weights. So like this is like the standard definition of regularization, but regularization gets applied to lots of methods that improve the ability of the network to at test time. So improve like the accuracy or lower the top 5 error rate in this case. That aren't just like changes to the architecture. So anything that you do that isn't a change to the architecture that gives you ability to generalize better in the test set is thought of as a regularization. Data augmentation is one of these. This is just standard now. People use this all the time. And so, right, like the way this works is you're given, like in these supervised classification problems here, you're given an image, you're given its label, you pass the image through the convolutional neural network, you compare it to the label, like its prediction to the label, and then you backprop that and you change your weights, and hopefully you're learning. So one way to really start to make, like especially in a task like this, one way to really make the convolutional neural network better and generalize better is to take your image and like make a whole bunch of derivative images from it. You know that they'll all have the same label. You use the same label as the original image, but then you just start doing all kinds of things to it. So there are standard things like, transforming. So like rotating it, flipping it about, either axis, so that's upside down, or it's just flip side to side, left to right. Changing the intensities of it, changing the colors of it, and then, so horizontal flips. This is a real interesting, real standard way to really improve on this ImageNet task, is to do these crops and scales. So, so if you remember, like the images when we, let's see, what did I say, like 277 by 277? I think that's what they were. Anyways, so what AlexNet did and what like everybody did afterwards was to do things like this. Was to take your image, rescale it so that the short side has some standard size like 256, and then you take these, you just randomly sample, in this case 224 by 224, some patch from within it. You can see some of like example patches, right? So there's like this patch right in here, this patch that's like the lower part, the upper part in the middle. These are all just randomly there, chosen there. And then each one of those is also a cat image. So now instead of your model being trained on 1.2 million images, now it can be trained on however many crops you do. So 5 times that, or 7 times that, or 9 times that, or whatever. And all of a sudden, it's like you have a whole bunch of new data to train on. And really, more data, more like well-labeled data, really helps your networks do better. It's like it's having, even though like obviously like the crops or the flips or whatever are very correlated with the original image, because you're doing these manipulations, it's giving the network, it's like decorrelating it in some sense from the original image and allowing the network to learn something, especially when you're doing these crops and these scalings. So like the procedure they were using here was to do random crops at train time, but then at test, what they would do is they would do the same kind of resizing, but then they would just take the 5 224 by 224 patches, again, because the network was trained on 224 by 224 patches, and you have to, at test time, use the same size. So what they would do is they'd take the 5 that were, so the 4 at each corner and the 1 in the center. That's what that's kind of trying to show there. And then horizontal reflections of each of those. So you had 5 patches and then 5 horizontal flips. And then what they would do is they take the output of all of those, all 10 of those, the softmax. That each one of those is a probability distribution, right? They'd average all those probability distributions. That gives you another probability distribution. And then they'd use that to make the prediction. And that really, really helped, really improved the ability of the network to perform well on the test set. So it really improved the ability of the network to generalize to images it hadn't seen yet.
Why did the coefficient calculate? You didn't capture the cat.
Yeah. So that's, so you would think like maybe we shouldn't do that because it doesn't capture the cat. So like in general that can happen. However, because you're doing so many of these, you'd expect that like of all the random prompts that you could do, you'd expect like most of them to have something cat-like in it. And so that would overwhelm like the crops that don't have cat in it, and you're still better off because you still have a lot more properly labeled data. It's true that it can happen, but you can see how that would be kind of hard with the choices that are made here, right? So if you resize, so the short size 256, as long as the height's not way different from 256, then these these 224 by 224 patches are basically like they're most of the image, right? I mean, at least on the short side, you're only missing 32 pixels, right? So like you don't really expect the object to like hide in those 32 pixels. Yeah. So making smart like size choices there is also important. Okay. Right, so you can kind of play around with the color a bit. So change the contrast, change the brightness. There's also like really more complex ways of doing things. So there's this idea of doing principal component color offset. So you PCA all of your data channel by channel, and you take your principal components. That's telling you like how much. So like in which direction the color's changing the most, and then you just change. So in that direction, you're basically just adding that color to. So adding or subtracting, you can pick some sort of offset or some sort of scaling factor there to change your image by. So basically, like in the direction of most color change, like throughout the training set, you just change the colors along that direction. So it's going to be some RGB vector, and you just change that way. And that's like some nice principled way of changing the color in an RGB image so that it's like you're like in some way like preserving kind of naturalness, like natural variation in the image. Anyways, it's used a bunch to do augmentation as well. And then the point here is like you might be sitting here thinking like, oh, I have lots of ideas like ways I can augment. I'm an expert at OpenCV or something like that, and I can do all kinds of things. And you're right. You can do whatever you want. You just have to make sure you have to think through. You have to think through like what do each of these transformations do they give me something like cat-like, or like do any of these transformations like now change my cat to a dog or something like that. So that seems kind of silly, I know, like that doesn't happen. So for these natural images, like a lot of these kinds of transformations are fine. But like in other applications, so like what we do at Recursion when we have images of cells, it's like geometries of the cells that often are important differences between cells. And so if you like take a picture of a cell and you scale it, that's turning it from like one type of cell into another one. That's not good. You don't want to do that. And it's kind of a simple example, but so you don't want to just like willy-nilly go and do this because you might be actually, without thinking about it, changing what the actual label ought to be on the image. But for these natural image data sets like ImageNet, all these things we're talking about are great. You're just going to get like a really stretched out cat or a really skinny cat or something like that. Okay, so that's data augmentation. Is that a question? Okay. Next is dropout. So dropout is another form of regularization that is used a lot in modern neural networks. So the idea of dropout is exactly as it says. You, as you're training your network, as you are doing the forward pass, you're basically you're choosing some probability at which each of the neurons in each layer of your network is going to be dropped out. Meaning it's not going to participate in this iteration of the forward and backward pass for this batch. And so, like, what you're basically getting is some subset of some subnetwork of your original network. Does that make sense? So you choose some probability and you say, okay, here's a batch of data. I'm going to do my forward pass, my backward pass. I'm just going to go through and I'm going to, with that probability, I'm just going to decide. I'm just going to say, hey, I'm going to sample a bunch of random numbers and say, okay, so this one is going to be here. This one's not. This one's not. This one is, and so forth. It's still going to be, fully connected through the remaining nodes, but we've dropped out all the nodes and all the weights that would connect to a node, to a neuron that we've dropped out. Weird, huh? You're like at every step, you're using a different subnetwork, randomly chosen from the full network. And it turns out this actually is like a really awesome way to regularize networks, so to make them better at predicting outside of the training set. So why is that? Yeah, so here's some pseudo actually full code for doing that. Okay, so why does this work? Well, the main thought on this is that it forces the network to have to produce a redundant representation of all the features. So it makes it really robust. So if you think about it, so like every time you do one of these you do this forward pass with a new batch and you get a new subnetwork, it could be that you have like the same batch every single time. So these different subnetworks are being forced to learn like the same, like to be able to resolve the same number of classes as any other subnetwork. So this is kind of really silly because like this is not how this works. We don't have a node that has an ear or has a tail, but you can kind of think of it as like learning features that in some abstract sense are starting to kind of capture what it is to be cat-like. And by doing this dropout, you're making it so that like there's not just like one neuron in here that is paying attention to the ear or the tail or the furry or like whatever the abstract feature is. There's no one neuron that's responsible for that. And what happens is that like in some sense they all need to evolve in some way so that representation is like more spread out throughout the whole network. That feature is more spread out and contained throughout the whole network rather than just in some like brittle single spot.
This is off topic.
Yeah.
However, from my understanding, dropout is patented by Google. Is there a legal concern with using this?
Everybody's like all these legal things to do. I've never heard that. That would be really interesting to know, but I've never ever heard of anybody being sued for using dropout. I think you're safe in an academic setting as well. Please use dropout. It makes your networks way more resilient.
Another thing on the legal thing, a lot of like Apple, Facebook, Google, they keep on patenting things that they don't necessarily like anticipate on enforcing because of other legal problems that they have to pass. So they're basically just like excessive amount of patents so that we don't get screwed over and end up getting sued for excessive millions of dollars.
Yeah. I just never heard of a dropout patent case, but maybe there has been one. These are interesting questions. Okay, so another way to think about this is that what's really happening here is that we're actually learning a large ensemble of models within one architecture. So every time we drop out and we get a new subset, it's like we have a different model. And so like one way to think about that is we actually have a whole bunch of different networks that, like at test time, they all kind of come together and they combine their predictive abilities to give us an even better prediction and lower generalization error.
So dropout like a weird way of batting or boosting? I forget which one it is.
No, because that's usually applied to the data, right?
Well,
boosting is not batting it, but yeah. So I mean, it's not like boosting. Let's see.
It feels like an ensemble kind of thing.
I mean, yeah, that's what I'm exactly trying to. I don't think it's definitely not like boosting, and it's not like bagging. It's just that you have. It's just that like there's a whole bunch of different subnetworks here, and because they're being trained as subnetworks, you can sort of think of like the final prediction where you use. Oh yeah, I didn't say this. When you're making predictions on the test set, you use all the nodes. You don't do a dropout at test time. So so you're using all the nodes. So you're basically like using all these like subnetworks all at once. So that's the ensemble idea there. It's kind of a loose analogy, and there's definitely like a huge number of. This is what this is pointing out. There's some huge number of subnetworks in a fairly large network. And we're obviously only like seeing some very small subset of those, but nevertheless, you get a whole bunch of these. And let's talk about this thing at test time. So another way to think about this is that dropout's making the output random because we are like randomly masking or choosing a subnetwork. And then at test time, what we want to be able to do is sort of average out that randomness, right? So it's like there's some probability with which we pick a particular subnetwork, and we want to just sort of like integrate over all of those to give us our expected output, and that's going to be somehow better. That is a very like hand-wavy kind of way to think about this, but it's important to use here because it really when you use dropout, you have to do something to your network at test time to make it actually accurately predict. And it has to do with this way of thinking about it. So just think about this very, very simple case where we have two inputs. They're connected by two weights to some output. This is all, let's do this as a linear case. So you can think of like the output at test time, which is this expected output, to just be the weight 1 times x plus weight 2 times y. And that's our expected output at test time. Like we're using the whole network. But during training, remember we had some probability of getting of dropping one or both of these weights out. So if we're using, like in this case, we're using like 1/2 as a probability of dropping the weight out, then there's a 1/4 probability that we didn't drop either. There's a 1/4 probability that we dropped out the second, a 1/4 probability that we dropped out the first, and a 1/4 probability that we dropped out both. So if you just do the simple math in this linear case, what you see is that during training time, the expected output looks like the test output, except it's multiplied by 1/2. Right? So actually, so these differ by 1/2. So actually, at test time, when we're doing dropout, we actually want to multiply, and notice that 1/2 actually corresponds to the probability of dropping something out. So during test time, we actually want to multiply our test output by 1/2, so that we preserve the size and scale of what was happening when we were dropping out during during training. So the way this looks is that at every layer in your network, you've done dropout with probability p. When you apply your your activation, in this case a ReLU, you want to multiply those activations by p, so that scales that back down. Otherwise, you'd have again, this is at test time, so I think I might have missed a training there. I apologize. At test time, you want to scale these back down, because if you don't do that, you'll get totally wrong answers. Because you're doing this to the output of each individual layer. So you might think like, oh, if I just did this at the end of my network, like that just scales everything, it wouldn't change anything. That's right, but you need to do this at every single layer, and so that that gets passed through the nonlinearities at each layer, and that starts to compound. So this is absolutely essential to do when using dropouts. Okay, so yeah, so here's some code for what that would look like at train and test time. We just saw the test time. Okay, that's dropout. Super important. Yeah, there's other kinds of dropout. So if for some reason you're just feeling like you don't want to put a times p in the predict here, then all you have to do is rescale your activations during training to divide by p, and voila, everything's back to normal. So it's just keeping track of the scale, right? So I have p outputs when I'm dropping out with size p. So if I divide by p, I like reboost those back up to the scale size, the appropriate scale size. All right. Yeah, and this is kind of a call out that this is like there are many types of regularization that look like adding randomness during training and averaging it out during test time. Okay, we are not done with AlexNet yet. There was another thing used here that we haven't talked about: stochastic gradient descent, but with a momentum term. So let's talk about that for a second. So we talked about stochastic gradient descent, where it's plain vanilla gradient descent, but then you do it with batches. So problems with stochastic gradient descent. There could be problems if, like for instance, your loss function at whatever points, like the gradient you're looking at whatever point you're on space, if it has a high condition number, which if you've done some numerical analysis, you know that these become really numerically unstable. This can happen when, say, like you have like a very steep direction in one. So in your loss function, you have like a steep part of your loss, and then like a very shallow part of your loss. And in that case, you'll get some of this kind of like horrible behavior. Like you want to go straight to this happy face, the local minimum, but you might jump all over the place, and if you have the wrong step size, the wrong roaming rate, this could be really bad. So there's a way to kind of deal with this and like other kind of minor issues with stochastic gradient descent. Oh, let's see. Right. You could also sort of get out certain small local minima. Forgot about that part, but let's not spend any time there. Okay, so also our gradients, remember they're computed on mini batches. They're noisy. That's actually a regularization, so that's good. But that can make it so it's hard to optimize as well. So there's a very simple thing you should basically always do in training, is to not use just plain vanilla stochastic gradient descent, but to add this momentum term. And the way this works, so here's plain stochastic gradient descent, where you have calculated you estimated your gradient from your mini batch, and then you update your parameters with some learning rate. in stochastic gradient descent with momentum, what you see here is that you actually have two variables that you're keeping track of. And you can kind of think of one as the term momentum kind of suggests. You can think of like what your weights as being like your positions in space, and then now you're going to introduce some sort of velocity. So like your gradient is like a velocity. It's a change in a certain direction in space. But now you're going to keep track of this velocity, and what we do here is we sort of preserve we like preserve some of the history of the gradient as we go along. So this line right here looks like plain vanilla gradient descent, stochastic gradient descent. It's just that our gradient term here is not just the gradient term that we've calculated, but it has some fraction of the previous momentum, or like lots of momenti. What's the plural of momenta? There you go. Momenta involved in it. So so like in the first step here, there's going to be no momentum, and you'll just get your gradient term. But in the next step, there's going to be your gradient term. You're going to add to that some fraction. And this row here is usually something between 0 and 1. You're going to add to that something about the last gradient step. And now, when you go to the next step after that, you will add to that. You'll take your gradient at that particular step, and then add to that some fraction of the previous momentum, which is going to contain gradients from the first step and the second step, and so forth. And so this is like an exponential moving average. If you've done this before, you're just kind of building up, just like you exponentially discount the gradients in the history by however many steps. So like maybe I should draw this out over here. What I'm saying. So if we have a pen. Yeah, so your momentum term. Oh man. Could I see a better pen? There's always been a red one here, but it's gone.
Catch?
Oh, good. Okay. Yeah, thank you. Okay, thank you. So, the first step, let's call it one. In the first step, you have just your gradient at whatever point in space you are. In your second step, you're going to have some fraction of the first step, or the first velocity, times the gradient here, and I said velocity momentum. And what this is rho times the gradient. And what I've been saying here is rho is somewhere between 0 and 1. So it's making it smaller. Right? And then our next momentum is going to be rho times v2 plus gradient at x3. And again, I can expand this out. So this is going to be rho squared at v1 rho squared at the gradient of f at x1 plus rho the gradient of f at x2 plus the gradient of f at x3. So the point is, so you can just kind of see what the pattern is here, right? So like Vn is some sum, not n, k goes from 1 to n, and these are all of the previous steps, and you have your gradient. I have that on the yeah, I have that. Oh, I have this the wrong way. N minus k. Something like that. So the point is that it's keeping around a history of all your previous gradients. But it's just like as you progress in space, like this is getting smaller, like the contributions from the ones a long time ago are just getting smaller and smaller and smaller. And the point of doing that is like it's just preserving some kind of history of saying that like, hey, I made a step in this direction like a while ago. I just kind of want to remember that I did that because like that might help me in future steps to kind of like stay in that, moving in that direction. And it turns out that, let's see. Oh, yeah, it might be programmed in different ways. So it turns out that when you do that, you get much, much better convergence. And I think I've got. I have a video somewhere. Well, okay. So yeah. So guess what it does? It makes it easier to jump out of local minima that are shallow, and certainly get away from saddle point because you're not just stuck there like in the saddle point where you would have zero gradient at that point because you got some history that didn't have zero gradient. Now you can actually move out of it. There's some different ideas here. What we just did was calculating the gradient at the actual step, but there are different ideas where, like Nesterov momentum, which is very similar, but it's like you're kind of you compute the gradient at the current velocity, kind of looking ahead to where you'll actually be. It's computed like this. So instead of the gradient being at your point x, like you normally would do, you take the gradient at x times rho times like the previous momentum. So yeah, this is used quite often as well, although probably not as much as just plain momentum. And let's see, we're running out of time. I can't remember what we have left here. Let me just check real quick. I think we're almost done. Okay, got it. All right, so yeah, this is just what's a good way to think about this? Like it says here, I didn't read this, but look ahead to the point where updating, where we are updating using the velocity will take us. So compute the gradient there and mix it with the velocity to get actual update direction. So it's like it's like using the history to like make an update and then compute the gradient there and then kind of go there. It turns out this is actually like it has nice properties in terms of like optimization and smoothing that out. Yeah, I do have this here. Good. So what I have on here are a couple of different. This is like a video. So you have some sort of lost surface. You see the star at the local minimum, and this is where we're starting from. So you're going to see a couple of trajectories of different colors. A stochastic gradient descent. So the red will be just using plain vanilla stochastic gradient descent. The green will be with the momentum term. The purple will be with the Nesterov term. There will be a couple other ones here that in the future we'll talk about. I won't say about today. Is added delta. But these are other ways of doing this optimization. But if I start this, yeah. Yeah. It's going to repeat itself a couple times here. So so let's just look here what's going on. So it's the same learning rate in all of them. But yeah, let's think about what's happening here. So first of all, you see plain stochastic gradient descent, right? It's going to the right spot eventually. It's just really slow, right? It's just using the local gradient to make a step. Now let's think about what happens with the green line, the momentum term. So in the momentum term, notice that it starts exactly the same way as the stochastic gradient descent, just as it should. Its first couple of steps are going to be mostly just like determined by those original gradients. But you can see it starts to make a really like large steps away from that in directions kind of correlated with the original direction. That's because as we're building up this history, we're remembering that we took steps in that direction, so we take steps that are more in that direction. direction. And they kind of go off, way off for a little while, right? Like they actually get farther away from the local minimum, but they kind of, get some different signal. They're like, hey, wait a minute, gotta turn around and head back. And they're faster because we're like there's the original gradient. There's the gradient from stochastic gradient descent, and then you're adding to it, rho times the momentum. So like that gradient actually is larger in some sense, right? Like you've added to that gradient something else. So like, as you're like starting to converge and get closer, you're actually doing like much bigger steps in the correct direction. And then you can see that the Nesterov term so the Nesterov term is actually converging faster. It kind of does stuff similar to the momentum term. It's doing it faster because it's doing this look-ahead thing. So it's computing the gradient at the point that we're at, and then with the original momentum term added to it. So it's like computing. It's like getting a gradient from the gradient you're getting here is like the gradient you're getting out here, because it's doing this like look ahead, right? So it actually starts to make like the right turnaround, for instance, earlier, because it sort of sees it needs to make that turnaround earlier. Yeah. Okay. So
on that last one, the green guy.
The green.
Yeah, the momentum.
Yep.
So since it's so steep at the beginning right there, that adds to its momentum and
Yep.
causes it to overshoot.
That's exactly right.
Is it a problem that it overshoots it?
It could be if like your learning rate sets it like leaves the look like the well that it's in, right? But that's the fun of the you assume that. Let me just quickly finish up. They use the learning rate of whatever, 1 10 to the minus 2, but they did this neat trick of reducing that by 10 every time their accuracy is plateaued, and then they did use an altitude weight decay. And then there's this historical note about the GPUs they were using had 3 gigs of memory, so they couldn't fit all the parameters into, they couldn't fit the full model into the memory of just one GPU, so they had it split up across 2, and so they actually split the filter mass. And so like in these layers that I'm pointing to here, these were split. In these layers, they actually were brought together, communication across the GPU. So like the gradients were passed across. And this is actually how now distributed training works, is you just pass gradients around from different subsets, but always bring different subsets of batches. Anyways, the point is, when they submitted this, they used an ensemble of 5 of their models to get a top 5 test error rate of 16.4%. Later on, after the competition, they did some additional tweaks and did a larger ensemble, and they actually were able to get that error rate less. But the entry that they made for that year, 2012, was at the 16.4 error rate level, and that won them. And one for them. And you can see that's a major, major improvement over the last year. So it's like 9-ish points of error there. So like a huge step forward from where this was previously. And so these next two lectures we'll go through the rest of these, and you'll see again major improvements to the point where we're doing so much better than humans that we have to get a new challenge in place. Okay, that's it for today. Thanks.